Hello, everyone. Um, Happy Wednesday. Um, Today we're going to be covering equality path constraints and interior point constraints. But before that, a bit of a programming announcement. I think next week we're going to cover like the newer methods, and then also kind of like what I consider good areas of research. I I plan on moving that new methods to our last lesson, and then in there I might touch on like areas of research, and that will give us another lesson in which we can do inequality path constraints next Wednesday. So today, just because it's a lot of material, today I'm just going to focus on the equality constraints. Yeah, I don't see why anyone would have an issue with that. And I think that just is a better spacing of time. So today, like I said already, multiple times, we're going to be covering all optimal control problems with path constraints. And then this generally, path constraints apply over entire trajectory. So it's kind of our definition here. So as before, we had constraints that applied to only the initial and terminal times. Then we also had kind of done path constraints but without dynamics. And then when we implemented dynamics, we implemented them kind of at all periods of time. That's like what we're going to do with the path constraints. And then also I'm going to touch on the end of this lesson, interior point constraints, which happen in the interior of the problem at some time, but don't apply to every time point, but only one specific time point. So as we start, we're going to kind of build up, and where we're going to start here is actually I'm sorry. Integral path constraints. So here we consider an optimal control problem with constraints so we basically integrate this n, which is some generic function, across our entire trajectory, and then we want that to be equal to some constant, so that this integral is equal to some constant. And this is actually kind of straightforward. We actually enforce this by adding another state. Oh, I apologize for my cursive. I'll go back to not cursive, just because I assume it's easier to read. So here we let y dot is equal to n, and then we also have initial and terminal conditions. So we could say y at initial time is 0, and y at final time is equal to k. So yeah, so now we just solve the problem as normal. So we have our Hamiltonian as before, with our co-states in, like, for traditional states and some dynamics. And then we have this new, where this new Lagrange multiplier mu that adjoins this n, which in this case acts as dynamics just as f. And really, the only reason I show this is to show that mu dot, which is the partial of the Hamiltonian with respect to that new state y, is equal to 0. Therefore, mu is constant. So when we do the other path constraints, we don't need dynamics for mu. Mu is a constant parameter. And then we have everything else. So this is just as before. So this is kind of like this is the simplest of this kind of more advanced constraints. And you might have even come up with doing this without being shown it. Okay. Stop me if there's any questions. But I'll be moving on to equality. Shouldn't have done my notes in cursive if I didn't want to write in cursive when I'm delivering it. Constraints of control variables. So instead of, see how up here we have some integral equal to something? Let me go all the way up here. Yeah, we have some integral equal to something. Now in this case, at every point in time, we don't have an integral equal to something. We just have some expression c that's dependent on time and control that's equal to 0. And then this is true throughout the entire trajectory. There's also a caveat where u is a higher dimension than c. So in principle, if c is, dimension 1, then you need u to be at least dimension 2. Otherwise, it's no longer an optimal control problem. Otherwise, it just turns into a normal boundary value problem. Or like, not bound, but yeah, it's like, then you kind of just go into not simple, but complex Lagrangian dynamic kind of area if you don't have at least one for u. And like before, there's two methods to deal with this. So we have an unenjoined. And then the way you do that is we eliminate some control variables through substitution of C equations. So this is kind of, so if C is of dimension 3, you could take away 3 control variables in principle by substitution. So this is kind of brute forcing unadjoined method. But what we're going to show here is the adjoined, in which, of course, we adjoin constraint equations to path cost. So of course you would do this with the entire functional, but you would join it to the path class, so then it shows up ultimately in the Hamiltonian, and then everything else appears the same when you do the derivation, which you can do in your free time. But I might include in the formal notes once I finally finish those. But in this case, we just have, yeah. So this is function of, well, let me not use the red under there. So we have our normal Hamiltonian plus this, which is our new kind of adjoined path constraints. And since C is only a function of time in the control, now I'm super inconsistent with the cosine. Should just embrace it, I guess. So since C only depends on time in the control, the only change to the optimality conditions is, so we have a dHdu, and if that's still equal to 0, right? But instead of what it was before, we have the partial with respect to the path cost plus the dynamics, which are adjoined, plus the term that is of a path cost. Okay, so there we have that. And now, not much more complicated. We have, I actually thought of skipping that first one. Not the first one, this one, the previous one, because this is nearly the exact same thing. But we have equality path constraints of control and state variables. So now we have C still, but we have C of time, state, and control. And then that is equal to 0. So we adjoin the constraint as expected. And then, so the optimality conditions, in addition to the ones derived last week, are, hold on, let me finish writing here. They are like the previous example. We have dHdu equal to 0, which then is equal to the same thing as before. But then we also have the co-state rates changing as well. So if you remember the co-state rate, the transpose of the co-state dynamics is the partial of the Hamiltonian with respect to the states that negated, which is in this case the partial of the path cost, the negative of that minus co-states times the partial of the dynamics. minus, and then now we have the constraint term. Okay, so these are fairly straightforward. Yeah, so once you join the constraints, yeah, it just acts as expected. And then it mimics what we did with the boundary conditions last week, in which we just adjoined the boundary conditions to the initial and terminal costs. So it's the same kind of thing. In this case, a Hamiltonian is to which we adjoin things instead of the other costs. Okay, this is where it gets more complicated. So I thought we had a lot, and now we might actually get out early. So we have a Crowdy constraints of functions of state variables. So we have some s of t and x only, and that's equal to 0. And you might think that it would be more complicated. Like this, it seems less complicated than what we have up here. But actually, when the control isn't there, it's harder to. I'll go through, but it's yeah, it actually makes the problem harder. So we could adjoin constraints as before, and that results in, so it results in the variation to the augmented cost functional being. And this is with all those other terms kind of already canceled out. But this is what is put in it, which changes. So just to indicate that there's all this stuff here, I'm going to put these ellipses. But see that this kind of term here, we have not only, as before, where we can set the derivative of the co-states to be the negative of this partial of h with respect to the controls. Instead, we have these other Lagrange multipliers in here, and this partial with respect to the constraints. So that's difficult to choose co-states and these other Lagrange multipliers simultaneously. And I have to admit that I was looking, when I was preparing these notes, I was looking for if you follow down this method, what it actually looks like and how difficult it would be to do numerically, and kind of went down a rabbit hole. It's because it's always presented the next way. But I'm going to actually do more reading on how this will look because I'm unsure which is the best to implement numerically. But basically, yeah, to set these, at least by hand, is difficult. And we have other methods to adjoin constraints too numerically, so it might be a moot point. But this next way is what's always presented in courses, so it's easier to convert to, actually let me add an extra word, constraint of state variables into, that's a bad into constraint of control and state variables. So basically what we want to do is we want to take this problem that we have here and convert it to the previous problem. And the way we do that is if, so this constraint is equal to 0, then we could take the derivative of it, which is equal to ds dt, which is, of course, well, not of course, but is the partial of s with respect to t plus the partial of s with respect to x times x dot, and then that's just a chain rule, right? And this is equal to 0 because the derivative of 0 is 0. And then we have this, I'll do one more kind of simplification. So we have x dot that's equal to f. And then if this derivative contains u explicitly, then we stop. But if it doesn't, then we continue. So let me write this note here. Let me write it bigger. Continue taking derivatives until control appears explicitly. And then we're going to assume that's q times. So continue taking these derivatives until we reach some s of q. S taken whatever that q derivative of s, and that's dependent on t, x, and u. We use explicit, and then that's equal to 0. And then this is actually what we use as our constraint. So we're going to use that as a path constraint, which is adjoined. So we could use this in place of the previous kind of problem formulation. The only other thing we need to add is if we just use this derivative of q, derivative of s, then we will your s your final s, like when you integrate these back, right? We'll integrate and we still have to maintain that each of these sub-steps is 0, because otherwise the integral might be a constant, and then because the derivative of a constant is also 0, and then that integral might be a line, and then you get a just like polynomial equation. So that's not what we want. So in addition, we enforce original constraint and other derivatives as boundary conditions at t is equal to t naught, or it could also be t is equal to tf. It's at your choice. You can do either one. But basically we have this factor here that is s of t of x, and then we have s, the first derivative, and that would also be dependent on t and x. And you basically keep going down until you have s of q minus 1, which is also dependent on t and x. These are all equal to 0. So then we have q additional boundary conditions. And this is all based on the assumption that q is less than or equal to n. You would have problems if you have more boundary conditions than states, but that's not really going to be the case, at least as far as I know. Okay, any questions on that?
Sean, can I just add on something?
Oh, yes, please.
Yeah, so Eli, Matt, and Winston, just to add on to what Sean said or what Sean has been teaching in this lecture so far, why do you think we need to study all this? The reason is that when you solve these real world problems, you will always have some kind of constraints. Like, for example, in the A4H project, you are dealing with angle of attack. We know that there are lower and upper limits to that. So when we start learning these things, we start with unconstrained because they are easy to understand. But we march on to these complex problems because the real world problems involve all these kind of constraints. And when you solve these more complicated problems, especially in hypersonic regime, then you have more of these different types of constraints. And Sean just talked about this Q, which is the order of the state constraint. You will see that there are different values of Q being 0, 1, 2, or more. So all that you will see in upcoming lecture, but just wanted to let you know that why we are actually studying all this. And another thing is, like, when we solve these problems in traditional way using indirect methods, we just solve 2 point boundary value problems. So we care about the initial point and the final point. But once you introduce all these constraints, you get these extra points, and then the problem is no longer a 2 point problem. It becomes a multi-point boundary value problem, and it becomes extremely complex and gets out of hand. So therefore, you will see these advanced methods in the upcoming lectures, which will ease your life. So you will appreciate that even more uh, after Sean goes through all these tedious process of how we set up these problems and solve that using traditional ways. So just wanted to add that to what Sean has been telling.
Yeah,
Thank you
thank you,
very
Kshitij.
much. I appreciate that. And it's also, so we do have these advanced ways to deal with these problems, but I think it's also important to see how it's done, because most of the advanced ways, they make solving really difficult problems possible, and I love them, and I recommend that everyone uses it so you don't have to go through this kind of tediousness. Because as I write down, like, mathematically, it seems it's easier to write down abstractly, but actually doing it is fairly tedious. But it's important to see the exact methods and kind of if you develop a new way to do something, or someone asks a question of like what kind of approximations you're taking, it's important to know where those will show up in traditional ways.
Exactly.
Just curious, is there anyone on this call who hasn't taken 550 with Dr. Crossley? Okay, looks like everyone took 550. So, yeah, we got a brief we got a brief overview of how constraints worked for timing variant problems, which is what 550 covered.
Yeah, so that's if and this is kind of foreshadowing. The method that like that I use most often to deal with path constraints, and the method which it's the method that Hittich developed. Basically, if you're familiar with interior penalty methods, that's what it boils down to, at least when you're dealing with state constraints. But yeah, if there's no questions on that, if there's no further questions, I'll go through an overview. And this is needed for next week when we cover. These equality path constraints are the easy ones, relatively. But this is all foundation for the inequality path constraints, which are actually what you're going to see in your problems. So, and another component we need to kind of preempt that are interior point constraints. So here we consider case where a set of conditions are specified at an interior point T1. And then theoretically you get T2, T3, T4, if you so desire. And I guess another comment on this type of problem is that there might exist. I'm not familiar, or nor have I used like a comprehensive alternative method to these interior point constraints. So if you want to develop one in the future, that might be an area to look into. So I'm going to kind of be consistent with our notation before. I'm going to define as psi. So this is like a boundary condition, but it's in at 1. So I'm going to say psi 1, and that's a function. I don't know why I made that I. That's a function of t1, and then x at t1, and that's where t0 is less than t1, which is less than tf. And kind of graphically, we have some function. This would be t, and this would be x. And we have like a t naught, t1, and a tf, and then our x would do something, right? And then this will be constrained, and then it would do something else here. And then this could kind of get even more complex, and you can take kind of interior point constraints and extend them to problems with interior point costs, and then extend them to problems with discontinuities in states that happen on interior points. But I won't really cover those. So the result, this results in 3 point boundary value problem. So as before, we've always had 2-point boundary value problems. This is a 3-point boundary value problem. And so we have minimize J with some initial cost, final cost, and here you could add your interior point cost too, but I'll just leave that out. And then we have our path cost. That's subject to x dot is equal to f, and then f psi naught is equal to 0. So these are as before. And then I'm adding this psi 1 is equal to 0 as well. Okay, and then we could, as always, we could adjoin constraints to cost, to the cost functional. And I'm skipping steps here, so we kind of have a combined initial cost, like the capital fee, or combined augmented terminal cost, big fee F, and then here we're using pi is our Lagrange multipliers, and we adjoin this interior constraint. And then this stuff in the integral, which is our Hamiltonian minus our costates times the dynamics dt. And then, as expected, these are Lagrange multipliers. Okay. And then one of the steps that doesn't match our previous derivations is that we can split this, we split this integral over the two intervals. So I'm just copying everything from above. Except now we have, that's copying too much. So then this is going to be T1 approaching from the left-hand side. And then we go from T1, but from the right-hand side to TF. And you can imagine if you have 3 or 4 or 5, as even more intervals, you can do the same thing. So, and then as you would expect, we can derive necessary conditions of optimality by taking differential of J prime. So I'm going to actually skip a lot of that. You go through and you do what we kind of did in previous lectures. And when I get the formal notes up, or even before if needed, I will have it kind of explicitly out, but just to kind of save time and people's patience, I'm just kind of go to the result. So we have dj prime And now looking how fast I'm going through this, I probably could have included it, but it doesn't. I'm probably happy I didn't. So then we have the partial. I used end up here, right? No, I changed it. Sorry. This is phi 1. And this is the. So this is kind of like the time component. So this is corresponded to the variation. That looks like an H, but this is time. So we have the Hamiltonian on the left side minus the Hamiltonian on the right side, plus this kind of partial term. I don't know if you saw that because this partial term here. If time is fixed, so if you know at what time the interior point is applied, then this doesn't matter because the T1 is 0. And then we have kind of the same thing, but with co-states. Wait, I'm sorry, as I'm looking at this, I think I missed something. Oh, okay. Yeah. So we have a co-states on the right-hand side of the boundary and a co-states on the left-hand side of the boundary. In that means that a co-states are actually going to be discontinuous. And then we have a Lagrange multipliers times the partial of that interior point constraint with respect to the states. And that's at T1. And here we're assuming the states aren't discontinuous. And lastly, we have, and this hasn't really changed, it's only included because we have two different segments. But in both we have that dHdu times the variation in D still exists. Not D, in U. So, and then this, I guess I should have said this before, this DJ is, prime is after setting lambda dot the other boundary conditions for lambda and T naught and TF. So if you remember that we had all the other necessary conditions, that this here, this DJ prime, is what results after you already set all those equal to 0. So out of these remaining necessary conditions, the first one, let me put this. So we can make the remaining terms vanish. So we have the second one, I kind of skipped ahead in my speaking, but we just set, those things in front of the differences. We set those equal to 0. And that's T1. Okay. So Brian, yeah. Now, this is actually, I can pull up an example, because I thought this would take a lot longer, but basically you can see from the first one that if the state in question shows up in the interior point constraints, that you have a jump in that corresponding co-states. Likewise, if time shows up in that interior point constraint, it doesn't show up. Wait, no, I'm sorry. In addition, if time shows up, you will have a jump in the in the corresponding in the Hamiltonian, which, as I said before, the Hamiltonian acts as a kind of co-state for the time. Okay. So, any questions?
Don't have any at the moment.
Okay, great. Okay. Well, let me pull up an example of it's really. Actually, I'm sure you guys don't have other things you want to do. I'll use the example as like one of the practice things because it's just a lot of constants and writing things down. And if there's nothing else, then I think that's it for today.
All right. Thank you, Sean.
Oh, you're welcome.
Thank you, Sean.
Thanks, Sean.